Welcome to Lesson 4 of Enhanced Electric Power Quality and Reliability. In this lesson, we're going to discuss SCADA concepts. So this is our old familiar diagram here, and I'm going to do a little review, talk about what we've already discussed in the previous lessons and how it relates to what we're going to talk to today. So this is our power grid, and of course we've got our generating assets up here that we'd like to monitor, and they feed power into the grid that goes into our users, our residential customers, our industrial power customers, things like that. And then we've also got our renewable generation that feeds into the grid as well. In our first lesson, we talked about all the smart grid fundamentals and the fact that the electric grid has evolved over time, become more complex, and at the same time we're a lot more dependent on it. And so we've developed this smart grid concept where we're going out and instrumenting our grid and using that information to better operate the grid and to troubleshoot our problems and to learn how to do new things with it. And in our second lesson, we talked about telemetry. And telemetry specifically about how what telemetry is, which is measuring all these pieces of information that we need to know and reporting them back to a central location. And so in telemetry we talked about the concept of data tags. So if I were to say want to monitor the voltage on a transmission line, I would create a tag for that voltage, and that tag would have certain metadata associated with it, like a minimum and a maximum and engineering units and things like that. And then in the lesson after that, we talked about instrumentation. So we talked specifically about how a potential transformer works and what it looks like, and how computer systems can measure physical things that are happening in the world and produce a digital representation of that. So there's where we are right now. We've discussed telemetry and instrumentation. Now we're going to discuss the computer systems that actually carry those measurements back to a control room, or SCADA systems. So if you're operating an electric grid, you typically have some sort of a control room or a control center that's going to look something like this. And here's where the computer's trying to represent everything that's going on in your grid so that you can operate it and maintain it and fix problems. You can see the huge computer screens there, and at this point you should understand that all the information that's being shown on those screens are tags. And that each one of those tags is showing a specific data point. You should also understand how the process of getting that number into a computer happens through the analog to digital conversion process. So here's a simple SCADA diagram. Up here at the top, these are the workstations and computer systems that are in the control room or in some sort of central monitoring location, like I showed you in the previous picture. And so that all that computer equipment sits on top of some sort of a communication network that then has devices that are out in the field making those measurements. And so these devices are either PLCs, programmable logic controllers, or RTUs, remote telemetry units. This is a nice picture here of a SCADA RTU. So this is something you might find if you were to go out to like an electric substation or anywhere out in the field that where you were trying to make measurements and do things. You put the computer systems in these little weatherproof enclosures and close them up, and you have power running to them and a communications line running to them, and they sit out there and do their thing. So that's a SCADA RTU. RTU, I've seen remote terminal unit or remote telemetry unit. I like the acronym remote telemetry unit because, obviously that's what it's doing, is taking measurements and reporting data back. In the heart of all this is the programmable logic controller. And a PLC is it's a small industrialized computer that is made specifically to measure and control real-world processes. So let me mark this up a little bit and get my pen ready. So a PLC right here, as you would see, right here is a CPU. This little card right there. These cards all plug in. If you look right here, there's a backplane. Okay, and so typically you put this backplane on the wall and or in your cabinet. And actually, I've made a mistake here. This isn't the CPU. This is the power supply. Okay. So usually these things run off of 24 volts DC, and so you have a power supply in here. Then you have the CPU, and then you have cards. Okay, and these are typically called I/O cards, input-output cards. And these are the things that are actually wired into the instruments and the field devices, and you might also have some sort of a communications card in there to talk to devices as well. So we talked about the analog to digital conversion process, and we talked about current loops, right? So the I/O cards all are, there's typically multiple types of I/O cards that are available for a PLC. You'll have analog input and output cards and digital input and output cards. So a digital signal would be like a digital input card. What you would do is you would wire, say, a push button switch to it, or maybe like a breaker closure or something like that. And so you could sense whether that button was being pushed or whether that breaker was closed, and that would be a digital input, right? Remember, our digital inputs are on or off. A digital output would enable you to close a switch, so maybe there's a motor out there or a breaker that you want to close, and so you would close the switch, and that would cause the action to happen out in the field. And then our analog inputs would be things like, maybe a 0 to 12 volt DC input or a 4 to 20 milliamp input, and that would allow us to take readings from the field. And then sometimes you'll also have analog outputs, so you might have a valve or something that was variable that you could close it, a quarter way or a halfway or, anywhere in between, and so you would have an analog output that would tell that valve how much to close. If you have a communications card in here, and we'll talk about that actually a lot more in our next lesson, but if you have a communications card in here, maybe you've got things like smart meters or some sort of smart device where the I/O, the actual A to D conversion is happening in the device, and then it's got some sort of a digital communications bus that can connect to the PLC. But if I go back to my original diagram here, let me talk about one more thing while I'm here. Okay, so here's the PLC in the cabinet, and then these down here are called terminal blocks, or TBs. And so typically what will happen is you put your TBs in here, and you'll wire from the TB up into the PLC, make it all nice and neat, and then out down on the bottom of the TBs, you'll have all your wiring going to your instruments and your devices out in the field. And then this right here is called Panduit, and it's actually kind of neat, but it's just to kind of hide the wires and make it all look neat so that you don't just have a jumble of wires when you open up a cabinet. Keeps you from snagging the wires and stuff when you're working in there. Makes the, not only makes it look nicer, but it's functional. So these Panduit this Panduit stuff, the cover just pops off right here, and then you can see all the wires in there. And then on the side, it's got these little fingers, so you can feed the wires out through it. But anyway, so the programmable logic controller here is kind of the heart of the system. They're little industrial computers. They sit inside the SCADA RTU cabinets, right here. So these are the PLCs inside the SCADA RTU cabinet. And then, of course, those RTUs are out in the field. So you can see in this diagram, it's got PLC and it's got RTU. A lot of kind of the same thing. So PLC programming, these PLCs have to be programmed to do things. And there's actually an international standard. It's called IEC 61131. And it basically defines the possible programming languages that you can use if if you choose to follow the standard, the ways that you can program a PLC. Their ladder logic, function blocks, structured text, instruction list, and sequential function charts. I see, out working for PLCs. Ladder logic seems to be the most common thing that you'll see, or in the most popular way of programming. And then when you get up into larger control systems, distributed control systems, and stuff like that, you'll see function block programming a lot. These are the two things that I see most often, are the ladder logic and the function blocks. In the next couple of slides, I'm going to show you a little bit what they are, or what they look like. Okay, so this is a ladder logic diagram. So this is what it looks like to program a PLC in ladder logic. I'm not going to go real far into depth here, but just the general concept, or these are your outputs, or the things that you're trying to make happen, and this is the combination of inputs that trigger that output. So in this combination, basically what would happen is if start and run are true and stop is false, then it closes a relay called run and starts a timer there. So anyway, it's not really important that you understand understand how to program ladder logic. I just want you to know, if you ever see this, or you ever see a PLC and somebody starts talking about ladder logic, you know what they're talking about. Ladder logic is one of the ways you can program a PLC. So function blocks, this is what function block programming looks like. It's another graphical way to program, and like I said, typically you'll see function blocks used more in distributed control systems. Like at the power plant, the main control system that's controlling the power plant would be called a DCS, a distributed control system, and it would typically be programmed using function block programming. Structured text. Structured text just looks like looks like probably what you'd expect computer code to look like. So it's a text based, whereas ladder logic and function blocks are both graphically based.